why do we care about space? It's a question I hear from time to time. Well, let me show you an image of the Milky Way galaxy. First of all, you'll notice that it's very pretty. It's very majestic. What's actually going on here is there's a supermassive black hole. It's located thousands of trillions of miles of kilometers away. So these are numbers that we are not used to in our everyday life. Our brains are simply not capable of processing how large the scale and age of our universe is. What's interesting is the further out we look into it, the more things we discover and the more mysteries arise. There are so many questions that still need to be answered. And people are motivated for this. We have people that want to figure out questions such as, is there life elsewhere? Curiosity here is an example of that. It is a rover that's been exploring Mars for the last 2 years, searching for evidence of life. Because we have questions such as, are we alone in this universe? And this image right here, that's Earth, right here, this little point. It's taken from Saturn, and it's a perspective that tells us that from everything we know, we are very alone here. This imposes a responsibility on humanity to learn and understand more about ourselves, life, Earth, and all the interconnections we find ourselves in the middle of. It's a revolutionary perspective for our species and one that gives us a great insight into our own future. The space age started in the late 1950s and eventually led to humans landing on the moon. This brought on a whole new wave of technology and optimism about the future. It brought on new technologies that eventually led to all the innovations that we're used to today. It encouraged many fields to push their own limits of what was possible. If we can go to the moon, what else can we do? Interestingly enough, this wasn't the greatest benefit of going to space. It was actually seeing Earth for the first time in human history. Suddenly, our planet became connected, finite, and vulnerable. It is a revolutionary perspective for our species, and one that gives us great insight into where we're heading. Mehdi and I are engineering students. We are being trained to become problem solvers. The role of engineers is to serve society for the better, and we do this by taking history's understanding of the way the world and the universe works. We need more than just engineers and scientists, but the whole public recognizing our global influences and planning for our common future.
Whenever I hear about space, I think about human cooperation. It's been always about that. Look at the International Space Station. Do you realize how massive it is? It's so big that you can even see it in the sky with your bare eyes. I even tried to take a picture of it, but obviously I got so excited and my hands shook. To just give you a better example, it's so big that it fits a football stadium. Or in more Canadian term, it's as big as 5 hockey rinks next to each other. Now, can you imagine how many people were involved in this project? It took engineers and scientists from different countries 30 years to build, to design, build, test, and launch this massive structure, segment by segment, into space. This is a true marvel of international cooperation. Now, why do we go to space? Now, why do we go to school? To learn things, right? But why don't we just learn everything on our own? Because we need school to push us to get to our goals, which is that paper at the end. But school alone is not enough. A school alone can't train a good engineer, or a scientist, or a lawyer, or even a teacher. You need experience. You need to gain experience. And you can get that from extracurricular activities. Extracurricular activities give you that extra push to do something that you wouldn't normally do. A good example of this is the Canadian Satellite Design Challenge, or CSDC. The goal of the competition is to build a tiny satellite. They call it a CubeSat. It's really as big as a loaf of bread. Very tiny, but yet very challenging. But surprisingly, the hardest thing about this is just to keep up with school. Now, when we all started, we had no idea how to do this. But the good thing about our our team was that 2 years ago, in the same competition, in the first edition of this competition, we had another team that participated. Their experience contributed greatly to our progress, which meant that we didn't have to spend all the time to start everything from scratch. We could spend more time on the cool science, like our scientific experiment. And that's how we learn the value of sharing knowledge. Because space seems intimidating to some of you, but the reality is, if we actually shared what we learned, we could make it much more accessible to people. And that's why we want to eventually make our projects open source, so that other students can look at them and learn from them, and eventually make them even better, come up with better solutions than we did. Nick?
So why is communication so important? Well, because unlike many other fields, space is at the limit of challenges. It is mainly due to the space environment we are dealing with. The first thing you notice when you go into space is there is no atmosphere. This causes phenomena such as outgassing. Outgassing is when gases dissolved in a material leaks out, and it can change the material properties and also affect other components. You wouldn't want your multi-million-dollar satellite to be useless because your lens is fogged up. Adding to that, there's also thermal cycles, which relative to the sun, the satellite can jump to really high temperatures and really low temperatures. It's designed for that. There's also radiation all over space, and only gets worse the further out you go. There's also something else we have to consider, and that's space debris. I'm not talking about the one that caused mass extinctions in the past. Those ones are predictable. It's easier to know when they're coming. Talking about micrometeorites. These are the smaller ones, less than a millimeter in size. They are whizzing around the planet, and you have no idea where they're coming from. You just know that they're going to hit you eventually, and they cause lots of damages. This brings us into our scientific experiment, the payload of the satellite. We are testing the healing properties of a self-healing material in space. This is research that's been going on for the last decade, and it's finally ready to be brought to space. We are taking this, and we are putting it into a satellite, and we find it's a very exciting payload. When the team was first deciding on which ideas or which experiments to test in the satellite, everyone thought this one was the coolest one. So everyone voted for it, except for the team that had to actually build it. This was because a mechanical experiment like this with moving parts was never done in a satellite this small. We had to learn on our own, go on the internet, read books, consult professors and other experts, and there's no resources that would explain how to do this. We had to improvise. And this was a whole process that we had to deal with. The experiment ended up being a 3-point bending test, which is how we damaged the material. This alone was a question of how do you damage the material, along with other ones as how do you know if it's actually healing? Because we can't put a camera up there for other reasons, such as space-qualified cameras are over 10 grand, and our budget, we're only students. Our budget is very small. So eventually, we went through the whole process. The main thing that hits you in the face when you start a project like this is you are consistently faced with failure. This was a short breakdown of a year's worth of failure every day, every month. And how this affects not only just this experiment, but the whole satellite is monumental. Because when we make a small change, and these are pretty big changes, when you make a small change, it affects the rest of the satellite. Because we are multiple engineers working from different fields on the same project. The lesson here is that we had to absolutely communicate very well.
Failure. Why do we put so much emphasis on failure? Because space technology is about being certain that it will work. Unlike other fields, once you launch a satellite, you can't really go up there and repair it. Well, you can, but it's very expensive. But the exception is Hubble Space Telescope. Once it was launched, there was a problem with it. So NASA had to send a whole shuttle mission to go up there and repair it. It was so dangerous and very expensive. But at the end, it was definitely worth it, because Hubble taught us a lot about our universe. And you can't really put a price on that. Now, building a satellite that goes up in space 700 kilometers and orbits the planet every 90 minutes is a big challenge. So our team of 20 students, once we started, we all had the same question. How do you build a satellite? So we had to just break it down in 2 steps. Launch. You're going to go up in there with a rocket that's going to accelerate up to 12 Gs. So you have to account for all the vibrations on the structure. You have to do a lot of calculations. And we have to do a lot of testing. Then, once we're in space, you have to think about how you're going to produce power to survive. So then, you have to use solar cells and then store all the energy on the batteries. But then, what's going to happen when the batteries get too cold? Because they're not going to work. So you have to think about keeping them warm all the time. We also have to think about communicating back to the ground to send all the information down. So we have to have a good antenna, which is actually made of tape measure. The thing is, keeping the cost down is a measure of success, right? On the other hand, we face the problem of how you're going to orient the satellite in space. Like, how do you do that? But then we realize we're living on Earth, and Earth has a magnetic field. So you can simply put a magnet on it, and that's going to do the job. It's a cheap solution, and it's been tried before, so it's very good. And then you have all these systems that are going to work together in harmony. But if you don't have a computer and a software to run everything, it's not going to be possible. You have to do a lot of coding and everything. Now, we had even more questions, like how to protect the electronics from radiation, how to locate the satellite when it's in space, how to come back from a failure if it happens, and a lot more questions we faced. And not all the answers are in textbooks. We have to rely on other people's experiences. And sometimes we have to come up with our own solutions. Our satellite costs around $30,000, and that's the cheapest we could go. It's much cheaper than other bigger satellites. And it's cheap because of the use of off-the-shelf components that you could easily buy online. Now, to give you a good example, is that we had to buy $8,000 worth of solar cells because these cells are the best in the world, and there's no other alternative for them. But yet, to keep the cost low, we had to go with cheaper connectors that only cost $20, a fraction of what it costs for the solar cells. If we had more money, we could have obviously bought space-qualified stuff that costs around hundreds of dollars or thousands of dollars. But this does the job, so we're good. Now, last year, we were thinking about doing a crowdsourcing on Kickstarter, mainly because why not? It's one of those things. It's one of those things when you start, you have no idea how it's going to turn out, just like the project. But to our surprise, it turned out very well. We actually raised $15,000 from people we never met. But even more important than that, we got a lot of messages of support that people told us how we were inspiring them. But honestly, it was them who were inspiring us. That's the power of people when they support science. That's the power of people when they support science. Now, this is one instance where technology allowed us to reach other people for a common goal. Now, another thing to mention about CSCC, and that's that CSCC has another goal, and that's educational outreach, which is to go out there, talk to the younger generation, and tell them about space. Believe me, kids love hearing about space. They get fascinated. And our goal all along this project was to make them a bit more curious about the universe and the space. And our goal today is to make you guys a bit more curious about space.
Educational outreach.
Yeah.
That's what we do.
Good.
All right. So space is this amazing barrel of mysteries. It has inspired people to go further and push what the limit of human knowledge can be. Our experiences are examples that space is still very new, and that we want to help and we want people to keep searching for answers, because we have all these questions that have been asked by humanity for thousands of years. We would not have been able to get this far if it wasn't for all the information, all the support from everyone else. And this is in the nature of big projects like this. It's how humans work. It seems to be the theme of this TED Talk so far. Connections actually matter, and they make a huge difference. Goals like this seemed impossible, but are now more of a reality, more accessible. Collaboration has allowed us to see further and do more. And as Isaac Newton said, if I see further, it is by standing on the shoulder of giants.
Thank you.
Cool. Please go on.